Hi, good morning all. Sachin, can you hear me?
Hello, sir.
Yes, Sachin. How
Hello,
are
sir.
you? Yes, Sachin, can you
Yeah,
hear
I'm
me?
fine, sir. How are you?
Okay, okay,
Yeah,
fine, fine.
it's I'm audible, sir.
Okay, okay. Okay, so you said you will complete all the videos. Did you complete it?
No, sir. I'm still four classes pending, sir.
That day you said no, you will complete all the videos.
Yeah, I tried my best to cover it up, sir. I'll finish it, sir.
Okay. So when you will complete all the things?
Yeah, fine, sir. I will definitely complete it, sir.
Okay. Srinivas? Yes, Srinivas. How is your day going? Srinivas, can you hear me? Okay. Yeah, Rajasekhar, anything, any confusion,
Nothing, sir.
anything, everything is
Nothing.
fine.
Yes, sir.
How is your project going? You guys did not met in the last week.
Yes, sir. Last week we were met. He did not come. This week we'll do, sir.
Do it, man, because times are passing quickly,
Yes, sir.
right?
Yes, sir.
Okay. So others will join.
Yes, sir.
Okay, then we'll wait for maybe 2 minutes. Then we can start our last video of this module, that is deflection and the conjugate view. So till now we have studied two methods for finding out the deflections and slopes in a beam. That was
Sir, your
deflection.
voice is breaking, sir.
Yeah, now is it better or still breaking?
It's good, sir, now.
Okay. So we have completed two method, right, to find it out the displacements and slopes in a beam. So today we'll discuss the last method, that is conjugate beam method. How many of you has watched this video? Conjugate beam method. Yes, anyone? No?
No, sir.
No. Shashidhar also joined. Okay. Shashidhar, who else? Others? Okay, so I'll just play this video. This is the last method to calculate the deflections and slope. I hope initial first both the methods you guys are clear with. One was double integration method, next one we discuss moment area method. And this is the last method we'll discuss, that is conjugate beam method. Okay, so I'm starting the video. Please stop me if anyone has any confusion in the middle. Welcome to the structural analysis course. So currently we are in a second module, that is to calculate the deflections and slopes in a building or in a beam basically. So before the classes, earlier classes, we have discussed what is the equation for the beams, and then using the equation of beam, we solved using the double integration method how you can exactly calculate the shear forces and bending moments on a structure. Then in the last class, we have discussed another method, that is moment area method, to finding out the deflections and slopes. And then we discussed what are the advantages and disadvantages of each method, in which situation you could use the double integration method, and in which case you use the moment distribution area moment area method. So in this lecture today we'll discuss the last method for the calculation of deflection and slope, that is conjugate beam method. So let's get started. So this method is based on the similarity principle of structural analysis. So what do I mean by similarity principle? So let's review first very basic things about the structural analysis. So for example, what is moment? So moment is no, we know that it is a force into distance, right? force into distance, we call it moment. So now if you have a very small moment we denote it as dm equal to v into dx, right? For a small distance, if you take a small section on a beam, so maybe a very small section if you take, then we can write dm equal to v into dx, right? Then what is v? So v is basically shear force, right? Shear force dm by dx. So this is one expression we can use, right? V is the shear force and dm by dx. So from simply this expression we can get it, this final expression, that is v equal to dm by dx. Now what is v? V is a shear force, right? V is the shear force. So now if you consider udl, like this w here, if this beam, if you consider, so this beam having a udl, w is acting on it, right? So what will be the shear force? So shear force or total force, already we know all these things, right? I'll just write it in a quick format. So if you convert this W into a point load or in a force, so what you can write? V equal to W into dx, right? What is W? W is the UDL. UDL means forces per unit area. And now if I consider a small section here, it is dx. Then how much total force acting in that small section dx? So that is W into dx, right? So that is nothing but our shear force at particular section. So shear force V also it can be written as W into dx. What is W? W is the UDL. So UDL means uniformly distributed load. Or okay, so that is basically force W into total length. You will get the total force acting on a particular segment. Okay, so for if the total length, this distance is dx, then how much total force acting in that? So W is the unit force per length, per area, per length, and the length here is dx. So total force acting in this small segment is W into dx. So our shear force V can be denoted into equal to W into dx. Okay, so these two equations now we'll use extensively. So that's why I just recapitulated both the equations. One is V shear force equal to nothing but dm by dx. This means change in moment, we call it shear force. So that's what dx dy dx. So that is a derivative of moment is nothing but a shear force. And similarly, shear force equal to w into dx. So these two expression now we'll use extensively in our equation. So this is the equation, dv by dx equal to w. So dv, so small force dv by dx equal to w. So that's what we have derived here. So from here, if you take a small segment, so it will be dv by dx is nothing but w. W is the UDL, uniformly distributed load in a beam, right? So this expression is written here, dv by dx equal to w. So w is what? W, this is a real beam. So real beam and w is as a UDL, right? UDL is acting upward or any upward direction we consider, okay? So w is acting, is a UDL, and then we can write dv by dx equal to w. Right, from this is the real beam, from this beam we can write this expression, right? Now from this expression again we know what is v. So from here we know that v equal to dm by dx. So if you substitute v value with dm by dx, what you will get? You will get d square m by dx square equal to w, right? Just if you substitute v with this expression dm by dx, so what you will get? D square m by dx square equal to this expression you will get. So from this real beam, so this is the original beam, which is simply supported beam. One end is hinge, another end is roller, and the UDL is acting. That is W is the UDL. Please note it down all the parameters very carefully. So here UDL is W, and total length of this beam is L given. Okay, so from here what we can write is dV by dx equal to W. That is change in shear force is nothing but W. That's what we derived also here. And from here, if you substitute the value of v equal to dm by dx in this equation, you will get this is the expression, d square m by dx square is equal to w. Right? These two expressions we have just now saw. So from this, and already we have derived the beam equation, right? What is the beam equation? In the last class we have derived. So beam equation we have derived d square y by dx square equal to m by ei. Right? This is the beam equation we have derived, and single derivative dy, single integration, if you take dy dx, we'll get integration m by ei, right? So this is the expression we have derived in the last class. So this is nothing but and so is theta. So theta is basically dy dx, right? So same thing now here we'll just use the similarity principle. So dv dx by we can just I'll just substitute here. So theta is equal to nothing but dy dx, right? So from this expression, what we can write is d theta by dx equal to m by a, right? So that we can derive from this expression. So because what is theta? Theta is dy dx, right? So here 2 times dy dx is there, d square y dx square. And what is theta? Theta is dy dx. So if you just substitute dy dx by theta, then you will get d theta by dx equal to m by e, right? This expression. So this is the original expression from the original beam we just computed, and this one is from the beam bending equation, right? So and this one also we have derived, and just now we saw this is a real beam, and d square m by dx square is equal to w. W is the UDL, and this is our original beam equation, right? D square v by dx square. V is nothing but y. So same thing you replaced here is y, v. So d square v by dx square is equal to m by a. So these are the two distinct expressions. So first expression is from this beam, and this one is for moment for this original beam, and these two actually we have derived from our beam theory, right? So now if you replace if you see the similarity between both the expressions, right? So dv dx equal to w, and here d theta dx equal to m by ei. So from similarity between these two, what you can do is so you can consider an arbitrary beam. So this is the real beam, and now imagine a arbitrary beam or a random imaginary beam. So this is an imaginary beam. Just consider the length is L, it is same, and this is an imaginary beam where UDL is acting. So this UDL magnitude is m by ei. Okay, so this is the expression. So from here, similarity between both, what you will get. So this is another imaginary beam where W equal to m by ei, whereas V is the shear force, but in the imaginary beam it is theta. Right? So when I'll solve a problem, this concept will be more clear to you. So this is just a similarity between from this beam to this beam. So this one is the original beam. So this beam we are talking about. And next, this beam we are talking about, this is a hypothetical beam. So this is not a real beam. This is an imaginary beam we have assumed, where we replaced W with a UDL now m by ei. So this is UDL is acting, and the magnitude here is m by ei. Okay, and the d theta by dx. So this is the imaginary beam. So in that imaginary beam, if we find it out, shear force V at any location, that will be actually the theta in a real beam. So similarly here also, if you see, this is a real beam, d square m by dx square. So this, if you see, both are similar equations, right? So if you replace m with a deflection y, then what you will get? So this is the imaginary beam. This imaginary beam, if you compute the moment at any particular moment, this particular section at any moment, so that moment is equivalent to the deflection in the real beam. Okay, so in other words, what I can say is this is a real original beam. So we can draw a similar imaginary beam which is very similar to real beam. If real beam UDL is acting W, then in the imaginary beam the UDL is acting as m by ei, right? So this is from similarity between these two equations we just drawn this imaginary beam. So this imaginary beam is nothing but called conjugate beam. So the one is the original beam, and from original beam we draw a conjugate beam. So in the conjugate beam, what is the loading? Loading is nothing but m by ei. So whatever m by ei diagram of original beam, that will be acting as a loading in the conjugate beam. So in the conjugate beam, now if you find it out shear force at any particular point, that shear force is equivalent to theta, slope in the original beam. Similarly, if you find it out moment at any point in a conjugate beam, this is equivalent to the deflection in the original beam. So we have a two theorem for this equation for this theorem. Theorem one is the slope at any point in a real beam is numerically equal to the shear force at the corresponding point in the conjugate beam. So there is two beam. One is real beam. So this one is a real beam, whatever we saw. So from real beam we have to draw a conjugate beam. So what is conjugate beam? Conjugate beam, the loading will be whatever loading is there. So this original beam loading is W. So we have to find it out the moment diagram of this beam. So M by EI diagram of the original real beam will be the loading in the conjugate beam. So now this is our conjugate beam. So in this conjugate beam, for example, you want to find out what is the slope at this point. So what will you do in the same point in the conjugate beam? What is the shear force? That shear force is actually equivalent to what is the slope at this point. Similarly, as per the theorem 2 in the conjugate beam, so whatever moment will be generated in the conjugate beam at particular point, so that same moment is actually equivalent to the deflection at the real beam. So using this method, first for what are the steps we have to follow? First one is original beam will be given. So we have to convert original beam into a conjugate beam. So basically we have to draw the M by EI diagram of the original beam. So whatever M by EI diagram you get, that will be the loading in the conjugate beam. And you have to replace the supports also. So next slide we'll see how you can replace the supports. So now once you draw the conjugate beam, so now it is very easy to find it out the shear force and bending moment at any point. So shear force and bending moment at any point will be simply the deflection and the slope in the original real beam. So let's see in the next slide. So how the supports are changing from real beam to conjugate beam. So if yeah, so did you guys understood what I was talking about here in the conjugate beam concept? So conjugate beam is nothing but imaginary beam. Right? This is the original beam which is having the loads, either it may be UDL or concentrated, whatever may be the load. This is our real beam. So in this concept or in this method, we have two types of beams. One is the original beam, which will be given to us, and another is the conjugate beam, which is the imaginary beam that we have to develop from the real beam itself. Okay, so this is original beam, and original beam we have after looking into original beam we have to draw a conjugate beam. So what will be the conjugate beam? How to draw conjugate beam? The length of the original beam and the conjugate beam is same. That is first point. Next thing is what could be the loading in the conjugate beam. So loading in the conjugate beam is nothing but M by EI diagram. So if you recall, last class we have solved one problem using the moment area method. There we have drawn M by EI diagram, right? So M by EI diagram will be the loading in the conjugate beam. So this original beam has W load, UDL is acting. Whereas in the conjugate beam, the loading is now M by EI diagram. Means you draw the M moment diagram of this original beam, and this you divide it by EI. That will give you the loading of conjugate beam. Right? This part is clear, or shall I repeat? Rajashekar, did you understood this part?
Yes, sir, almost.
Okay.
Sir,
Shashidhar, yes, Shashidhar, tell me.
sir, you told you have to draw M by EI diagram, no, sir?
Correct.
Can you just explain it how to we do exactly?
In the last class, we solved one problem using the momentary method. There we have drawn M by A diagram. How exactly you have to draw? That is simple. You know BMD diagram, right? Bending moment diagram. Any beam,
Yes, sir.
first will be draw the bending moment diagram. So that bending moment diagram is nothing but the M by EI diagram. If you divide the coordinate by EI, you will get M by EI diagram.
Okay,
Okay.
sir.
So very simple it is. Last class we have solved in details. Anyway, in this problem also we will do it. So M by EI diagram of the real beam is the loading of a conjugate beam. So in the real beam, you have the W loading, but in the conjugate beam, you have the loading M by EI diagram itself. Right? So that is one thing. And then support also will be changing. So in the real beam, if it is a fixed support, then in the conjugate beam, it will be free support. That we'll see in the next slide. But for in this slide, you have to understand there are two beams. One is real beam and there is a conjugate beam. The conjugate beam loading is nothing but the M by EI diagram of the original beam. And now our main objective is what? To find out the slope and deflection, right? Our main objective is to find out the slope and deflection of a real beam. So slope and deflection of a real beam can be easily calculated if you find it out the conjugate beam. So once you draw the conjugate beam, at any point where you want to find it out the moment, or sorry, where you want to find it out the deflection or the slope in a real beam, at that location in the conjugate beam, find it out what is the shear force and bending moment. So in the conjugate beam, whatever will be the shear force and bending moment at a particular point, the same value will be equivalent to the slope and deflection in the real beam. That is explained here. If you see the right side in analogy. So in the conjugate beam, whatever is the V means shear force, the same thing will be the theta, means slope in the real beam. Similarly, whatever will be the moment in the conjugate beam, that same thing will be deflection in the real beam. So once you draw the bending moment, once you draw the conjugate beam, and if you find it out the bending moment and shear force at any point, that is nothing but the slope and deflection in the real beam. So it is very easy to calculate the slope and deflection using this method. Just draw the conjugate beam. Once you draw the conjugate beam, find it out shear force and bending moment at any point where you want to find it out the deflection and slope. So that shear force and bending moment value is directly give you the what is the deflection and slope in the conjugate beam. Okay, so that is on theorem 1 and theorem 2. So theorem 1 says the shear force in the conjugate beam is equivalent to the slope in the real beam, and theorem 2 says the moment in the conjugate beam is equivalent to the deflection in the original beam. So that's what, very simple. Anyone has anything to ask? Is it clear? Okay, if it is clear, then I'll just playing this video. So now you understood, right, how to draw the conjugate beam diagram. But now one thing you have to notice that support also will be changing. So in the real beam, if the support is simply support, then in the conjugate beam also it will be simply support. There is no change. But if in the real beam the support is fixed support, then in the conjugate beam it will be free support. So like that support also you have to change. So that will be see you will see in the next slide here. Okay, I'm playing the video. Real beam. So let's do conjugate beam. So if in a real beam, if a support is pin joint, so in the conjugate beam also support will be pin joint. There is no change. If a real beam the support is roller support, then in the conjugate beam also support will be roller support. Why? In the real beam, whatever is theta and delta, theta is slope, delta is deflection. Conjugate beam, same parameter is basically shear force and moment. So in the real beam, so this is a real beam. So this is in real beam, this is a pin joint, right, or hinge joint. So hinge joint, there is no deflection, deflection is zero, but slope is not zero. Already we discussed in the earlier classes. So slope at this point is not zero, whereas deflection is zero, right? So, but in the conjugate beam, deflection is equivalent to moment. So moment is zero, as slope is zero means moment also zero, but deflection is not, slope is not zero. That's why shear force has some value, right? So that's why it is the same pin support. So similarly, roller support also there is no change in the conjugate beam, but in the fixed support. So this is a real beam fixed support. Fixed support has zero slope, zero deflection, right? But in the conjugate beam, it will be free. If in the real support, if it is fixed, then in the conjugate beam, that end will be free. There won't be any support. Similarly, in the real beam, if it is free end, then in the conjugate beam, it will be fixed end. Right? So these are the conversions. What is the real beam and what is the conjugate beam? What the support will be. Why? Because, for example, if you see this fixed case, so in the real beam, it is fixed. Fixed means there. How much is the reaction? How much is the delta? Deflection is zero at this end. Slope also zero at this end. So correspondingly, in the conjugate beam, shear force also zero, moment also zero. Right? That means this is a free, right? There is no reaction. There is no reaction moment. There is no reaction force. That's why it is free in the conjugate beam. So now let's see how we can convert a beam into a conjugate beam. So this one is a real beam. Real beam, this end is hinge. So in the conjugate beam also, this end is hinge. There is no change, right? So whatever real hinge means hinge, both are same. So there is no change. Only change will happen if real beam, if the end is fixed, then conjugate beam, it will be free. So for example, this beam, if you see, so this is a real beam where one end is fixed. So basically, this is a cantilever. So this end is fixed and this end is free, right? But what about the conjugate beam? So in the conjugate beam, this end will be free because see, if real beam end is fixed, then in conjugate beam it will be free, right? So that's why here it is free. Whereas in the real beam, if the end is free, then in the conjugate beam it will be free. So that's why in the real end, this end is free, but in the conjugate beam, it will be fixed, right? So similarly, all the things, all the beams you can see, all the supports, how you can convert from real to conjugate. So now let's see the procedure for analysis, how exactly you can do. So our first step will be obviously to draw the conjugate beam. So first you have to transform the support. So in the if it is a fixed support in the real beam, then conjugate beam it will be free. And if it is free in the real beam, then conjugate beam it will be fixed. That's what we saw in the last slide, right? So our first step will be to draw the conjugate beam. So in the conjugate beam, we'll just first we'll draw the support and then you apply the loading. So what will be the loading in the conjugate beam? So loading will be simply M by EI diagram of the real beam is nothing but the loading in the conjugate beam. So once you draw the conjugate beam, then using equilibrium equation, find out what is the reactions at the conjugate beam, and then find out the shear force and bending moment. And that will be equivalent to the slope and deflection in the real beam. So our main objective is to find out the slope and deflection in the real beam. So what we'll do, we'll draw a conjugate beam. So in the conjugate beam, at that point, we'll find out what is the slope, what is the bending moment and shear force. So that value will be directly give you what is the slope and deflection in the real beam. So let's solve a problem here. So then the concept will be clear to you. So the example here is determine the slope and deflection at point B of a steel beam shown in figure. So this is a figure shown in figure. This is a steel beam. And see, this end is fixed and this end is free. So basically this is a cantilever beam where only single load is acting at the center. So you are
Yeah, so did you guys understood the support, how supports are converted? I hope it is clear, right? So let me just again explain this part once again. So in the before you understood, right? There will be a real beam and we have to draw a conjugate beam. So what will be the length of the conjugate beam? It is same as a real beam. So real beam, whatever length is there, L, conjugate beam also same length. So there is no issue. Now next is the loading. So what will be the loading in the conjugate beam? That we have seen that M by EI diagram in a real beam is nothing but the loading in the conjugate beam. Okay, so now you know how to draw, how to fix the loading in the conjugate beam. Now in the next question is how will you draw the how the support will be changing now? Support. So this is a table, and that also I have explained how this value also came. So if in a real beam, if it is a pin support, then in the conjugate beam also it is a pin support. So there is no change if it is a pin. Now in the if in the real beam, if it is a roller support, in the conjugate beam also support will be roller. So there is also no change here also. Next. If in a real beam, if it is a fixed support, then in the conjugate beam, it is a free support. Okay. And if it is a free end in the real beam, then in the conjugate beam, it will be fixed end. Please remember these few cases. Now, if you see the example here, right side. So this part, these all beams are real beams and right side beams are conjugate beams, right? So if you consider first beam, so this end is hinge support, right? So in the conjugate beam also it is hinge support. So similarly, if you see this is a cantilever beam. So cantilever beam means this end is fixed, but whereas in the conjugate beam, this end will be free. Similarly, the right end in the real beam is free, right? No support is there. Whereas in the conjugate beam, this end will be fixed. So like that, you have to convert all the supports from real beam to conjugate beam. So that's where it is explained in this slide. And next we discussed what is the procedure for analysis. First, you have to draw the conjugate beam and then you calculate the shear force and bending moment diagram in the conjugate beam, that will directly give you the slope and deflection in the real beam. So over. So here now I tried to explain one example. Please watch this remaining part. If anyone has any doubt, please ask. Please.
Slope and deflection in the real beam. So what we will do, we'll draw a conjugate beam. So in the conjugate beam, at that point, we'll find out what is the slope, what is the bending moment and shear force. So that value will be directly give you what is the slope and deflection in the real beam. So let's solve a problem here. So then the concept will be clear to you. So the example here is determine the slope and deflection at point B of a steel beam shown in figure. So this is a figure shown in figure. This is a steel beam. And see, this end is fixed and this end is free. So basically this is a cantilever beam where only single load is acting at the center. So you are asked to find out what is the slope and deflection at point B. So after you apply the load 5K, your beam will buckle, right? Beam will buckle. So what could be the deflection at point B and what is the slope at point B? That actually we have to find it out. And E and I, both the values are given to us. So our first job will be what? Our first job will be to draw the conjugate beam. So this one is a real beam. Now we have to draw the conjugate beam. So first what we have to do, we have to convert the support. So in the real beam, if you have a fixed support, so in the conjugate beam, that end will be free. There won't be any support in this end, right? And if in the real beam, if there is no support, means if in the real beam if it is free end, then in the conjugate beam it will be the fixed end, right? That's what we saw in the last slide also, how you can convert the supports. So now this is the reverse cantilever. If you see, this is the original cantilever, this end is fixed, this end is free, but in the conjugate beam it is just reversed. Left end is fixed, left end is free and right end is fixed. So the support now we have just converted. Now we have to draw the loading. So what will be the loading in the conjugate beam? Loading will be the moment diagram, right? M by EI diagram of the original beam will be the loading of the conjugate beam. So what is the moment diagram of this beam? So moment diagram, so if I draw here the moment diagram, right? So load is acting here, right? So load is acting here, so which is creating and clockwise moment at B. So clockwise moment, how much it will be? 5K is the force, 5 into 15, right? Total 75 moment will be generated at this end. So this is the moment diagram. So okay, I'll just make it here. Yeah. So this is the moment diagram basically. So 5 is acting here. So whenever you go this side from right to left this side, so here you will have the maximum moment. How much it will be? Moment will be 5 into 15. So 5 into 15 is 75. That's what 75 is acting here, right? So this is the moment diagram. So this moment diagram is nothing but the loading in the conjugate beam. So this is a conjugate beam, and the loading, if you see, loading is nothing but the moment diagram of the original beam. So this is the original beam's moment diagram is this one. This moment diagram is now acts as a loading into the conjugate beam. So over, now we drawn the conjugate beam. So this end is 75 by EI. How we got 75? 75 is 5 into 15. So total moment, how much is generated here? Right? So this is conjugate beam drawing is over. So now we have to find it out how much is the shear force. So our question is what? We have to find it out the slope and deflection at B. At this point, we have to find it out the slope and deflection. So in the real beam, whatever is the slope and deflection, in the conjugate beam, that will be the moment and the shear force. So in this conjugate beam, if we find it out what is the moment at this point and what is the shear force at this point, so that is actually equivalent to the slope and deflection in the real beam. So now we have to find out what is the moment and deflection at this point, at this B dash point. That is same to same, that is equivalent to the theta and delta, slope and deflection. So now what is the shear force here? So theta B is what? Deflection, which is nothing but equal to the shear force at BB dash. So theta B equal to BB dash. So what is the shear force here? Shear force will be simply the area of this triangle. How much is the area? Area will be half into base into height, right? So half into base is 15 into height is 75. If you just compute half into base into height, so let me just write it here. So area will be half into base is 15 feet, 15 into height is 75 by EI. So if you compute this value, that much is the shear force acting at this point, VE. And that is nothing but this much, this one. Right? So this is now if you substitute E and I value, which is given to us, E and I value, you will get this is the final expression. So this is the shear force, conjugate beam. So which is this is actually shear force in the conjugate beam, shear force here at this point, which is nothing but equivalent to the slope in the real beam. So real beam slope is equivalent to the shear force in the conjugate beam. Similarly, real beam's displacement is nothing but the moment in the conjugate beam. Now we have to find it out what is the moment at this point. So once we know the moment, that is equivalent to the displacement at point B. So moment will be how much? So moment will be force into distance, right? How much is the total force? Force is this much. We computed half into base into height. So this is the force into distance will come. Distance, CG distance. So CG distance will be how much? So CG will be lying somewhere here. So this distance, this entire distance, this distance. So it will be 15 plus 2/3 of 15, right? It will be in a 2/3 of CG. 2/3 of 5, 15, right? 2/3 of 15 will be 5. So this is 10. 10 plus 15, so total will be 25. So that's what is written here. If you see 25, so this area into 25 will give you the moment at B, right? Area into distance. Area is already, you know, this is the area, and distance is 15 plus 10, 25. So that total value will give you the moment at B, which is, so in conjugate beam, whatever is moment in the real beam, that is the deflection. So this is the deflection at this point. So if you just substitute EI value, you will get this is the final minus 1.5, 1.05 inches. So deflection will be happening at B end is 1.05 inches. So that's what. So it is very easy to calculate using the conjugate beam method. So whatever original beam will be there, our first step will be to convert original beam into a conjugate beam. So we have to convert first support. If it is a fixed support, then we have to make it into free. If it is free, then we have to convert into fixed. If it is a roller, then there won't be any change. If here it is roller support, then here also it will be roller support. If here it is hinge support, then conjugate beam also it will be hinge support. So last slide we saw all these things. So after you convert support, then next you have to apply the load. So what will be the load in the conjugate beam? That will be the moment diagram of the original beam is equivalent to the loading in the conjugate beam. So whatever moment diagram you will get from the real beam, that will be the loading in the conjugate beam. So once you draw the conjugate beam, then simply wherever the question asks to find that out, shear force, deflection and moment. For example, question asks deflection and moment in the center point. Then you have to find it out what is the moment and shear force at this in the conjugate beam at this point. So that will be the equivalent to slope and deflection in the real beam. So that is also a very easy method to solve the deflection and shear force, deflection and moment, and deflection and slope at any beams. So that's what we have completed our second module, that is the calculation of deflection and slope using the geometric method. So in this total we have discussed three methods. First one is double integration method. Next one we discussed moment area method, and today last method we discussed, that is conjugate beam method. Thank you.
Yeah, so did you guys understood this method or this example?
Yes, sir.
So it is very simple, right?
Yes,
Chandrasekhar?
sir. Much
So-
easier than the direct integration method and
Yes, it
moment.
is comparatively simpler. Correct.
Yes, sir.
So whenever you have a beam, first try to draw the moment diagram, right? M by EI diagram you have to draw, and support also you have to change. If it is a fixed support, you have converted into free. Free means fixed. Now this is our conjugate beam. One is real beam. Similarly, draw quickly conjugate beam. So now after you drawn conjugate beam, now it is very easy. So in this conjugate beam, whatever will be the shear force that at that point, for example, at the middle, you have to find it out. In a real beam, you have to find it out what is the slope and deflection at the center. That is our question. Maybe at center, you have to find it out slope and deflection. So what will you do? Quickly you draw the conjugate beam. So once you draw the conjugate beam at that point, at the center, find it out how much is the shear force and bending moment in the conjugate beam. So whatever shear force you will get it, that shear force will be directly, that same value will be the slope. Whatever shear force you will get it, that is the slope in the real beam over. And whatever moment you get it in the conjugate beam, that is directly give you the deflection in the real beam. So it is very easy to compute all the deflections and shear force in this method. Yeah. What about Shashidhar? Did you understood this method? Shashidhar, can you hear me? Okay. What about Sachin? Sachin? Sachin, where you guys left?
Sir, they're texting, sir. Texting in the chat box.
Oh, they are messaging. Eh?
Yes, sir.
Okay. Yeah, Shashidhar, did you understood? Please unmute yourself, no? Then quickly we can, if any doubt is there, quickly we can complete it off. Just unmute yourself and speak. So, any confusion till now? Just a second, okay. What about Sachin? Sudeep joined just now.
Sir, I understood, sir. It's a bit easy than compared to the previous ones.
Okay. So, what you understood? Can you explain to me quickly? What is this method?
One second, sir.
Yes. Where did you left? Chinna, are you there?
Yes, sir.
You understood the method?
Yes, sir.
What you understood? Tell me. Tell me, man.
Yes, sir. Sorry, sir. Actually, some noise was coming. I went to other room.
No, okay, that's okay. I'm speaking with Chinna first. Okay. After that, I will come with Shashi.
Okay, sir. Sure, sir.
Yeah, Chinna, tell me what you understood. Chinna, no response.
Yeah, it's we need to find the slope and deflection, sir.
One
And
second, Sachin. One second, 1 second. I'm speaking with Chinna first. Yes, tell me. Unmute yourself and speak. Yes? I don't know what happened to you. Okay. You're Shashidhar, yeah. You just unmute yourself and tell what you understood.
Yes, sir. Sir, earlier we were using double integration method, sir. Now we are using conjugate method. In this, we will convert into that bending moment into M by EI method.
What is M by E method? I mean, can you just explain the method quickly? What exactly you have to do?
So that method I need to learn, sir, again. That old video I need to watch it.
So in this method, what you are getting?
Sir, we'll draw the bending moment, sir. Then we'll draw the M by A diagram. And after
Yeah.
drawing it, we'll find
Rajashekar,
the
I'll come to you. Rajashekar, I'll come to you. I'm just speaking with Shashidhar first, then I'll come to you. That time you can answer. Yeah, basically what you are finding out? Slope and deflection, right?
Yes, sir.
So in the conjugate beam, how will you find it out, slope and deflection, using conjugate beam method?
Sir, by drawing the bending moment diagram in the form of M by EI.
Okay. So in that conjugate beam, okay, fine. You understood the method?
Yes, sir. And it is also distributed throughout the beam.
Not distributed. What is M by A diagram? That same will be. If it is M by A is distributed, then loading also will be distributed. So depending
Okay.
on the M by A diagram. Okay. What about Sachin now? Sachin, you tell me. In Sachin,
Sir, can I speak now, sir?
Yes, you can speak now. So in the conjugate beam, if it is slope, in the conjugate beam, if it is shear force, then what is this parameter in the real beam? Whatever you get it slope, I mean, whatever the shear force you get it in the conjugate beam, this is equivalent to what in the real beam?
Equivalent to.
Yes. Hmm? I explained so many times. I said same thing.
Sir, I think it is equal to slopes. Yeah.
Is it
Sir,
equal
is
to
it correct?
slope?
Yes, sir.
Then
For
how to
as
find out the displacement?
how to find the displacement, sir?
Yes, in the real beam.
How to find it? By using the moment.
Moment of what? Okay, who can answer this question?
Sir,
Sudeep,
moment
are
of
you
M by
there?
E, sir. By using the diagram M by E, we need to find the moment of M by EI.
No, not M by E, right? Not M by E. Okay, anyways, Sudeep, can you tell me how to find it out displacement in a real beam using the conjugate beam method? Sudeep,
Yes, sir.
yes, tell me how to find out displacement in the real beam using conjugate beam method.
Sir,
Hmm? Who can answer?
Sir,
Chinmay
I
did not
think,
answer. Yes, yes, Rajashekar, tell me now.
sir, the movement in the conjugate beam will be equal to the deflection, sir.
Correct. Very simple, right? That's what I was talking from beginning onwards. So in the conjugate beam, find out shear force. That shear force is nothing but slope in the real beam. So in the conjugate beam, find out what is the moment. That is nothing but the displacement in the real beam. So very simple. And so many times I said the point. Okay, anyway. Vishnu, what you understood from today's class? Vishnu? Vishnu, can you hear me? Okay, Srinivas, can you hear me? Srinivas or Nitish? Please unmute yourself. Srinivas, Nitish, Vishnu. Srinivas, Nitish, Vishnu. Last time I'm calling. Just unmute yourself and tell what you understood. Very simple. I am not asking difficult questions. Hmm? Okay. So fine. If you guys are not unmuting, then it's okay. So okay, now so you understood this method. So fine. So in the next week onwards, we'll start. Okay. So we'll solve one problem maybe on Monday. In hand, we'll try to solve it one problem using this method, and then I'll post new videos also. So we till now whatever deflection, slope and deflection we have completed, that is using the geometric method, right? We use three methods to find it out the slope and deflection. So in the next videos, next set of videos, I'll try to explain how to calculate slope and deflection using the energy method. We'll discuss more in details how we can do it using the energy method. Okay, so that we'll discuss energy method. Then our last unit will be remaining, that is how to solve the indeterminate beams. So all the beams, whatever we are solving till now, all are determinant beam, which we discussed. Now, what is determinancy, what is indeterminacy at the beginning. So all the beams, whatever we are solving, that is the determinant beam we are solving. So in the next week, or maybe after this last unit, we'll discuss how to solve the indeterminate beams. Okay. Okay, fine then. If no one has anything to ask, then we can close it off this session. Okay, thank you.
Thank you, sir.
Thank you, sir.
Hey, Chinnu. Hey, Chinnu. Srinivas.